Yo, what's up, science class fam? I got a little video lecture for you here. We're gonna call this one Hardcore Ice Cores. So, let's kick it old school with some paleoclimatology. Well, what is paleoclimatology, you might ask? Well, it's the study of the climate way back in Earth's history. But you might think like, well, how did they do that? Because we didn't have science and humans and technology back then. So since it's not possible to actually go back in time to see what climates were like, scientists use imprints. They were created during past climates. These measurements are known as proxies. Some climate proxies include things like ice cores, tree rings can even be used, and even things that we call sediment cores. And sediment is basically like the soil beneath our feet. So we can take a core or a cylinder of the soil beneath our feet or of the ice and figure out what the layers tell us. Some ocean organisms can also be used as proxies, such as diatoms and even corals. So scientists combine all the data that they collect from these various proxies to reconstruct records for past climates. Now, three forms of proxies that are commonly used in paleoclimatology are, first, lake sediments. So sediment cores usually from lakes can be analyzed in many ways. Charcoal trapped in sediments can indicate past fire events. Remains of organisms, such as those diatoms or micro life forms, and even pollen within the sediment can indicate changes in past climates, since each species has a limited range of habitable conditions. When these organisms and pollen sink to the bottom of a lake or ocean, they don't really decompose because of the water above them protects them from the air. So they become buried within the sediment. Thus, climate change can be inferred by species composition, or what species are actually in these different layers of the sediment. In this picture, you can see that there's definitely some banding happening between the layers of sediment. Each of those little lines there show different information about what was happening at that time that that layer was deposited. You can even see that some of the layers are deposited at different angles, which indicates some type of geological event. Now, another type of proxy would be tree rings. Tree rings can be counted to determine the age. I'm sure you've done this where you start in the middle and you count the different rings as you move out, and each ring tells you how old the tree was. The thickness of each ring can be used to infer changes in the temperature and even precipitation. Since optimal conditions for certain species will result in more growth, then the thicker rings would mean that there's more growth for a given year. Shorter rings would mean that there's tougher conditions for growth, and therefore that can give information as well. Even scars and burn marks can indicate past natural events like fires. But the best one, because it gives us the most rich data about the atmosphere's composition of gases, are the hardcore ice cores. Because they provide scientists with 800,000 years of climate data. This is how they are able to extract the ice cores. They bore a hole into the ice sheet in Antarctica and Greenland to extract cylinders of ice. Now they have to do it in Greenland and Antarctica because those are places where ice has accumulated over long periods of time. We call these our ice sheets. Now, they place those cylinders of ice into tubes that can be stored in a freezer so that they can be sent to science labs that are then able to analyze the ice. And a lot like the tree rings, we can look at the different layers of ice to understand what happened in past climates. So, various chemicals are trapped with the snow at the surface of the ice sheet. For example, after a large volcanic eruption, sulfuric acid and even dust and other types of dust from that volcanic eruption is deposited from the atmosphere and can show up in these ice cores. As the layers of snow are buried, the individual crystals of snow eventually, somewhere around like 200 to 300 feet deep, that pressure joins them together to form a solid matrix of ice that has air bubbles trapped inside it. These air bubbles contain a sample of all the gases in the air from the time that it was compacted. So this will collect things like that's in the air, like the nitrogen that's in the air, the oxygen, or the argon, are three most abundant gases in our Earth's atmosphere. The air bubbles can be cracked open to analyze what the ice, can be cracked open to understand what was in the air after the ice core is removed from the ground. Lots of different chemicals can be measured that give information about the extent of past sea ice, volcanic activity, the strength of the sun, winds, and many other different environmental conditions. Information from ice cores is then compared to other paleoclimate proxy data from sediments, corals, tree rings, and mineral deposits. So we take all that information to try to paint a picture of those past events. Since we didn't have humans around, we didn't have ways to collect this data. It collected for us in a way. So some of the most famous ice cores have been collected in Antarctica. The ice core that contains enough layers of ice to provide scientists with 800,000 years of data. That's right, 800,000 years of data was extracted from Antarctica at the Dome C location. So Dome C is also known as Dome Circle, Dome Charlie, or Dome Concordia. So you can see why they kept the C, Dome C. It's located in Antarctica at an elevation of 10,607 feet above sea level. So you can just think about how much ice then is stacked on top of each other to reach that type of elevation. It is one of the several summits or domes of the Antarctic ice sheet. Another famous site, though, that's also provided a lot of data, this one has 400,000 years of data, was extracted from the Vostok site, which you can see in those two locations there. Both of these are maps of Antarctica. One shows more of a world view, one shows the Antarctic view, but you can get an idea that there's this dome that forms that creates lots and lots of layers of ice that we can then drill down to the ice, extract those cylinders, and then analyze the data. So, at a much longer time scale, Antarctic ice cores have shown that temperatures there varied between warm interglacial periods. So those are going to be the peaks in the data. Those are going to be our warm periods because we're looking at temperature and CO2. So in those warm periods, we have warm periods that are interspersed with the colder glacial periods. So down here at the bottom of the graphs of these waves in the graph, that's when we would have had our glacial periods. So the ice cores have shown that temperatures varied between warm interglacial periods and colder ice ages. Basically, it looks like it happened almost every 100,000 years. So almost every 100,000 years, we had a new interglacial period followed by an ice age. The ice cores reveal an incredibly tight connection between temperature and greenhouse gas levels through the ice age cycles. And what I mean by that is you can see that the red and the blue line almost match with each other. Now scientists have decided to pair these two together because they match so well together, and that is CO2 and temperature. They have a very strong correlation with one another. So, if we look at the global average then, we can get an idea of where we are today in comparison to the past 800,000 years, but this is on a global scale and not just looking at Antarctica. Humans are responsible for adding huge quantities of extra CO2 to the atmosphere, and it's been at an alarming rate. The speed at which CO2 is rising has no comparison in the recorded past. The fastest natural shifts out of ice ages, remember those low periods when it was really cold? The fastest natural shifts out of those ice ages saw CO2 levels increase by around 35 parts per million over 1,000 years. Remember that, 35 parts per million over 1,000 years. That's what we noticed in the past. Before the Industrial Revolution, the natural level of atmospheric CO2 during warm interglacial periods was around 280 parts per million. The frigid ice ages, which caused ice sheets thousands of feet thick to build up over much of North America and Eurasia, had CO2 levels of around 180 parts per million. It might be hard to believe, but humans have emitted the equivalent amount in just the last 17 years. So we are seeing 35 parts per million increase over 1,000 years, but since humans have been around and we have been burning fossil fuels since the Industrial Revolution, we have increased 35 parts per million in just, that's right, 17 years. fossil fuels? Yeah, that's right. Burning fossil fuels, such as coal, oil, and natural gas, takes ancient carbon that was locked within the earth as a sludge from ancient plants that never fully decompose, which is why we call them fossil fuels, because we can burn them for fuel, but really they're just fossils of old plants. So it takes that ancient carbon, it puts it into the atmosphere as CO2, or carbon dioxide. Since the Industrial Revolution, humans have burned an enormous amount of fossil fuel, causing atmospheric CO2 and other greenhouse gases to skyrocket. Now currently, we measure carbon dioxide levels at an observatory on Mauna Loa in Hawaii. Mauna Loa was originally chosen as a monitoring site because it's located far from any continent. Therefore, the air that is sampled provides a good average for the Pacific Ocean region. Being high in elevation, at 11,135 feet, it is able to sample the atmosphere above the layers of pollution from human activities, which you can see here. There's the clouds, and you can see that this observation station is almost just right here at the clouds, or even above the clouds, because it is so high in elevation in relation to the areas around it. It even has snow on the ground, and this is Hawaii. Whoa! So being high in elevation, it's able to sample the atmosphere above those layers of pollution, but sometimes it's contaminated from local volcanoes. But if it is detected that local volcano sources are in the data, then they remove that volcanic data from the background data, and they take those spikes out that are from those local events. So again, the Mauna Loa Observatory is in Hawaii, and it's very, very far from any other type of landmass, or especially any big cities. So it's a really big advantage to be able to have a station that's out in the middle of the Pacific Ocean. So the Mauna Loa Observatory has been measuring CO2 since 1958. And it's been monitoring and collecting data relating to atmospheric change, and is known especially for the continuous monitoring of CO2. In 1958, the amount of carbon dioxide in the atmosphere was less than 320 parts per million. Over the past 60 years, the CO2 concentration has risen over 80 parts per million, and now it's even greater than 400 parts per million, which is more than we've ever seen from any of the climate proxies over the last 800,000 years. Notice that the overall trend of the graph is increasing. But every year, there's a high and a low temperature that creates a trend that looks like a sine wave. And I don't mean temperature, but I actually mean there's a high and a low in this actual graph data. There's a high and a low, then a high and a low, and a high and a low, and a high and a low, and so on as it goes up. But it continually goes up. So this is related to the fact that during the summer in the northern hemisphere, there are trees with leaves and other plants that remove the CO2 from the atmosphere through photosynthesis. And the data that's collected then shows the drop in CO2. So all these low points would be measured during the summer, whereas the high points would be measured during the winter, when there's less trees and leaves to be able to pull CO2 from the atmosphere, and there's not as much photosynthesizing happening. So more CO2 builds up in the atmosphere. Now, even though there are seasonal changes to CO2, this graph still helps show that the overall trend in the data is steadily increasing from year to year, and it is at an all-time high compared to the past 800,000 years of data. Temperature and CO2 are related to one another. More CO2 means more greenhouse warming and higher temperatures on Earth. Less CO2, then there is less greenhouse heat trapping capacity, and the temperatures decrease. Based on this relationship between the variables, we can expect that the overall average temperature of our Earth will increase as more CO2 enters our atmosphere. Now here's a different graph. This one shows us the rate of manufacturing in the past. This graph is helpful to see how humans are causing the release of greenhouse gases in our atmosphere. As we've been learning in class, companies and factories design and build products and burn fossil fuels in the process. This graph shows how much manufacturing has increased since the early 1800s. This is about the time that the Industrial Revolution began. The Industrial Revolution, in case you didn't know, was the transition to new manufacturing processes in the period from about 1760 to somewhere between 1820 and 1840. So this basically was the process of going from hand production and to having machines. And so instead of like picking plants in fields with the people's hands, they were able to have machines that could help do some of this labor and some of the work. There's also new chemical manufacturing, iron production, the use of steam power, the development of machine tools, and also lots of factories started to become really popular. So the industrialization led to the creation of the factory. The factory system contributed to the growth of cities as large numbers of workers came into the cities in search of work. Steel is often cited as the first of several new areas for the industrial mass production, which kicked off the second industrial revolution around 1850, which we can see here on the graph. The second industrial revolution gradually grew to include chemicals being produced, petroleum or oil being refined and distributed across the world, and in the 20th century, the automotive industry started to become more popular. The increasing availability of affordable petroleum products and oil also reduced the importance of coal and further widened this process of industrialization. But those are all fossil fuels that are being burnt and contributing to our greenhouse gases. Now, the Model T was produced it was released around October 1st, 1908. Sometimes it's referred to as the Tin Lizzie or the Leaping Lena or the Flivver. So next time you get in your car, you can just say, let's get in the Tin Lizzie. And it was produced by the Ford Motor Company from 1908 until about 1927. It's basically the first affordable automobile, and it opened up the ability to travel to the middle class of America. Some of this was because Ford's assembly line was able to produce a lot of cars, and a lot of people were able to buy them because they were more affordable, so lots of Americans started to drive. So this graph shows just that. It shows how the automobile has increased in popularity since it took over the horse and buggy mode of transportation. On the y-axis here, the percent of U.S. households that own an automobile. Today, most households own an automobile, which increased dramatically from the 1940s when only about 50% of households owned an automobile. And now currently it's 100%, if not more, because a lot of homes own more than one automobile. All automobiles burn fossil fuels and contribute to the greenhouse gases in our atmosphere. Even electric cars must be plugged into an outlet, and most people get their electricity from power plants that burn coal, a fossil fuel, to create energy. Therefore, our transportation industry is a major emitter of our greenhouse gases. Actually, 34% of all carbon dioxide is emitted from our cars and transportation industry, and another 34% is emitted from electricity. The rises in CO2 are a direct result of humans burning non-renewable fossil fuels, which emit greenhouse gases into the atmosphere. As of 2017, the average CO2 level was 405 parts per million, which is higher than any concentration that was measured from any of the climate proxies investigated by scientists. Although the global greenhouse gas emissions are at an all-time high, we humans have the ability to limit our greenhouse gas emissions and influence the future of our Earth. Scientists use models, which are typically used when it's either impossible or impractical to create experimental conditions in which scientists can directly measure the outcomes. The models of our Earth's average temperature predict what temperatures could be around the year 2100. As you can see, if we continue to emit the same amount of greenhouse gases in our atmosphere as we are today, then the temperatures will increase much more dramatically. If we choose to reduce the amount of greenhouse gases we emit, then the average temperatures will level out and will only slightly increase over the next 80 years. It's the scientists who collect the data and share it with the public. But it's up to you, the people, our corporations, and our governments to make the decisions to make a difference. So ask yourself, what are you going to do to make a difference based on what you've learned? Here's my web citations where I collected all my information. And I'm out. See ya.